Okay, so you know that feeling, right? Like when you're just glued to a show on Netflix,
Uh-huh.
and then you decide, hey, I'm going to move to the tablet. Yeah, maybe I'll go to a different room.
Yep, yep.
Hit play, and it picks up exactly where you left off.
Yeah,
It just feels so seamless, so magical almost.
it really does.
Or how about those recommendations, right? Sometimes they're so spot on, it's kind of creepy.
It is. How do they know?
It's like, how do they know what I want to watch next?
Right.
Well, it's not magic, it's data.
Yeah.
A truly mind-boggling amount of data. We're
Yep.
talking about something like 140 million hours
Wow.
of viewing data every single day flowing through Netflix's system.
Every day, that is a lot.
It's crazy. And think about it, your own binge-watching sessions, all those clicks, the pauses,
Oh, yeah.
every episode you devour contributes to this massive flood of information.
What's really fascinating to me is not just the sheer volume,
Right.
but the fact that it's continuous, right?
Yes.
It's not just a snapshot. It's 140 million hours every single day.
A constant stream.
Yeah, a constant stream of time-sensitive information.
Right.
So Netflix has to capture its store,
Right.
but also make it instantly accessible to power those features you were talking about.
Exactly.
That resume watching,
Yeah.
personalized recommendations. It all hinges on this data.
That's exactly what we're going to dive into today. So for this exploration, we've got some amazing insights directly from the source,
Okay.
the Netflix tech blog, where
Awesome.
the engineers themselves talk about how they design and maintain this colossal system.
That's great.
And we're also going to be looking at some fundamental principles from the Apache Cassandra documentation.
Perfect.
So our mission is to understand the technical marvel behind how Netflix manages this Everest of data.
Right.
But we're going to be focusing specifically on viewing history,
Okay.
yours and mine,
Gotcha.
and all the clever engineering that makes it all work so smoothly for us.
Like a backstage pass.
Exactly, a backstage pass. We're going to start by examining Netflix's initial approach,
Okay.
how they first tackled this data explosion.
Right. Then we'll look at the challenges they faced as their global audience just skyrocketed.
Makes sense.
And most importantly, how they strategically evolved their storage architecture to what it is today.
It's a story of evolution.
It is. It's a story of innovation driven by this constant need to scale
Yep,
and optimize relentlessly.
I like it.
So let's go back to the beginning when Netflix first started grappling with this massive amount of viewing data.
Okay.
They made a pivotal decision. They chose Apache Cassandra.
Cassandra.
Now, for those who aren't familiar, Cassandra is a type of database.
Right.
But the big question is, why Cassandra in the first place?
That's a great question. And the Netflix team themselves highlighted a few crucial factors.
Okay.
First off, Cassandra offers a remarkably flexible structure.
Okay.
Unlike some of those more traditional, rigid databases,
Yeah.
it could handle this constantly growing number of viewing records for each individual user
Right.
without getting bogged down.
This flexibility was key because, the information they might want to store about a viewing event wasn't necessarily fixed.
Right. Could change.
Exactly. It could evolve over time, and Cassandra could adapt to that much more gracefully
Okay.
than a database with a strict predefined schema.
Gotcha.
The second thing was that their data exhibited a very specific pattern,
Okay.
a lot more writes than reads.
Okay. Explain that a little bit more.
So every time you hit pause or start watching something that's a write operation,
You're right.
it's writing data to the database.
Writing it down.
Yeah, and compared to that reading data, like when you're looking at your history,
Uh-huh.
or when Netflix is pulling data for recommendations, that happens much less frequently.
Interesting.
So the ratio they were seeing was something like 9 writes for every single read.
Wow, 9-1.
Yeah, and Cassandra is known for its exceptional write performance.
Right.
So it was a very natural and efficient choice for this kind of workload.
That makes perfect sense when you think about it.
Yeah.
Every pause, every start, every completed episode is a write operation.
It is.
It's being written down somewhere,
Uh,
and then the reads happen when you're actively looking at your history,
right.
or when Netflix is in the background working its magic to generate those recommendations.
Exactly.
Okay, so the third reason why, Cassandra.
The third really important reason was their approach to data consistency.
Oh, okay.
Netflix made a deliberate trade-off.
Okay,
They prioritized availability and speed.
got it.
Their priority was ensuring that you could always access your watch history and continue watching your shows without interruption.
Right.
Even if there was a very slight delay in the data being perfectly synchronized across all their global systems.
Like a tiny little lag.
Yeah, you wouldn't even notice it.
Okay.
And Cassandra supports this with a concept called eventual consistency.
Eventual
Yeah,
consistency.
it's a bit of a mouthful, but
Yeah.
basically it means that all copies of the data may not be instantaneously identical,
Okay.
but they will all eventually catch up and become consistent.
Got it. So it's like a little bit of a grace period.
Exactly.
It's eventually going to be the same, but it doesn't have to be right this second.
Right. And this was a crucial decision for Netflix
Okay.
because it allowed them to maintain a highly available service, even if it meant these occasional imperceptible delays in data synchronization.
Interesting. So they're really prioritizing that seamless user experience over absolute perfect data consistency at every millisecond.
Exactly.
Okay, so they've got Cassandra, this flexible, fast-writing database.
Uh-huh.
How did they actually go about organizing all this viewing history within Cassandra?
Good question. So initially they went with a pretty straightforward data model.
Okay.
Imagine a massive digital table.
Okay, a big spreadsheet,
Yeah, kind of like that, where every single user has a unique ID.
their customer ID.
Exactly, their customer ID.
Okay.
And under that unique ID, each movie or show they watched was stored as its own separate column.
Okay, so each viewing event gets its own column.
Yeah, think of it that way.
Okay.
And to handle the millions of users,
Right, of course.
they implemented horizontal partitioning.
Okay, what is horizontal partitioning?
It's basically splitting that giant table across many different servers.
Okay, so instead of one massive server,
Right.
they're splitting it up.
Exactly, spreading the love. So no single server gets overwhelmed by the sheer volume of data for all those users.
Okay, so it's distributing the load.
Yes.
Okay, so every time someone watches something new, it's basically like adding another column to their entry in this giant distributed table.
That's a good way to visualize it.
Okay, so then how do you actually see your viewing history?
Right. How do they get all that information back out?
Yeah.
So they started with a few different methods.
Okay.
The simplest approach was retrieving the entire viewing history for a given user.
Okay, just give me everything.
Yeah, just dump it all. But if you were a relatively new subscriber, this was generally pretty quick.
Okay.
But for long-time dedicated bingers, this became really inefficient.
Because there's so much.
Yeah, as the number of columns associated with your customer ID just ballooned.
Oh, I can only imagine for those who have been with Netflix since the very beginning.
Yeah, those must be some massive records.
Yeah, so what did they do about that?
So to address that, they implemented the ability to search by a specific time range.
Okay.
So like, show me everything this user watched in the last month.
Okay, more targeted.
Exactly, a more targeted approach.
Makes sense.
But the performance could still vary quite a bit.
Okay, depending on the activity.
Yeah, depending on how much viewing activity occurred within that specific time frame.
Okay.
And then they also used what's called pagination.
Pagination.
Yeah, so instead of trying to load your entire viewing history at once, they would fetch it in smaller chunks or pages.
Okay, bite-sized pieces.
Yeah, exactly. And this prevented the system from timing out due to massive data transfers.
Right, that makes sense.
But it also meant that it took a longer overall time to see your complete history if you had a very extensive one.
Yeah, that makes sense. So while writing all that viewing data into Cassandra was efficient, reading it back out, especially for those longtime users, with vast viewing histories that started to become a bottleneck.
Yeah, that's precisely right.
Okay.
And as Netflix's subscriber base grew and the total hours of content watched climbed dramatically.
Yeah, more and more people watching more and more things.
Exactly. They started encountering some serious performance limitations with this initial approach.
Makes sense.
One key issue was the increasing number of what are called SS tables.
S-stables.
Yeah, stand for sorted string tables.
Okay.
And these are the immutable files that Cassandra uses to store its data.
Okay.
But over time, a single user's complete viewing history could be scattered across hundreds, even thousands of these individual files.
Okay, so it's fragmented.
Yeah. So for every read request to retrieve a user's history, the system might have to scan a huge number of these files spread across multiple disks.
Oh, that sounds slow.
And that naturally slows things down considerably.
Okay, I'm trying to picture this.
Imagine having all your notes for a project scattered across hundreds of individual scraps of paper
Okay.
instead of neatly organized in a few well-labeled folders.
Right.
If you want to find a specific piece of information, you'd have to rummage through all those scraps.
Oh, that sounds like a nightmare.
Yeah. And that's kind of what's happening when read requests have to scan so many SS tables.
It's like trying to find one specific grain of sand on a massive beach.
Yeah, a great analogy.
Okay, so it wasn't just the reads that were affected.
No, it wasn't.
Yes.
Cassandra also performs essential background maintenance tasks.
Right? To keep things running smoothly.
Exactly. Things like compactions, which is the process of merging and optimizing those SS stables,
Okay.
and repairs to ensure data consistency across all those distributed nodes.
Right.
But as the volume of data grew massively,
Yeah.
these crucial maintenance operations also became more time-consuming and resource-intensive.
Okay, so it's like the bigger the house gets,
Uh-huh.
the longer it takes to clean.
Exactly. And this further impacted the overall system performance.
Got it. So how did they initially address this issue?
So their first major step was to introduce a caching layer called EV cache.
EV cache.
Yeah. And the core idea here was to store the most frequently accessed viewing histories in memory
Okay.
in a highly compressed format.
Got it.
So they wouldn't have to hit that slower Cassandra database every time a user wanted to see their recent activity.
Okay, so it's like a shortcut.
Exactly.
Right.
So when you watch something new, that update would be written to Cassandra for permanent storage,
Right.
but it would also be merged into a compressed version of your history stored in that much faster EV cache.
Okay.
And if your viewing history wasn't found in the cache, a situation known as a cache miss.
Cache miss?
Yeah, Netflix would then retrieve it from Cassandra, compress it, and store it in EV cache for future faster access.
So EV cache acts like this readily available, super fast, short-term memory.
Exactly, for our viewing habits.
Or the stuff we're actively engaged with.
That's a great way to put it.
Okay, but I'm sensing a but. Date.
You're right. EV cache did a lot to reduce the load on the Cassandra clusters.
Yeah.
But as you might anticipate, it wasn't a perfect long-term solution.
Right.
Especially as Netflix continued its hyper-growth, it had its own limitations.
Okay, so this brings us to the next stage of their data journey.
Right, the introduction of what they called the live and compressed storage model.
Live and compressed.
Yeah, so here, the Netflix engineering team made a really fundamental observation.
Okay, what's that?
They realized that the vast majority of users mostly access their recent viewing activity.
Makes sense.
You're typically resuming something you watched yesterday, or maybe looking back at what you finished last week.
Yeah, I can't remember the last time I scrolled back more than a few weeks in my continue watching list.
Exactly. And while your older viewing history is still valuable for things like long-term recommendations or for your own personal records, it's just not accessed nearly as frequently.
Yeah, it's kind of like an archive.
Yeah, exactly.
Okay, so based on this understanding of user behavior.
They made a decision to split each user's viewing history into two categories.
Oh, okay, two buckets.
Two buckets, each optimized for its specific usage pattern.
Okay, tell me about these two buckets.
So the first one they created is called live viewing history, or live VH.
Live VH.
Yeah, and this is for all the recent, frequently accessed content.
Okay, the recent stuff.
Exactly. And this data is kept in an uncompressed format, which makes reading and writing super fast.
Gotta be fast.
Yeah, absolutely critical for that seamless experience of pausing on one device and resuming on another.
So this is like the fast lane.
Yes, exactly, the express lane for data.
So my current shows the movies I'm in the middle of, all that lives in this live VH.
Precisely.
Okay, what of the second bucket?
Right, so the second bucket is for all the older stuff titles you watched months or even years ago and access less often.
Okay.
And they name this compressed viewing history, or compressed VH.
Compressed VH.
Yep, and as the name suggests, this older data is heavily compressed to save storage space.
Makes sense.
And improve the efficiency of this less active data tier.
Got it. So my viewing history is essentially split into these two buckets,
Yeah.
each optimized for how often I need to access it.
Right.
So how did this translate into technical differences?
Okay, so because live VH needs to be incredibly fast and always up to date, they tuned its underlying Cassandra storage with more frequent compactions.
Compactions, you mean those SS stables we talked about?
Yeah, exactly. Remember those?
Vaguely.
So more frequent compactions mean fewer SS stables to search through.
Okay, less clutter.
Yeah, exactly. Keeping those read latencies low.
Gotcha.
They also implemented a very low garbage collection grace period.
Garbage collection grace period. That sounds interesting.
It's basically a waiting period before old data marked for deletion is actually removed.
Okay.
A low grace period means they're aggressively cleaning up space in live VH.
Okay, so it's like taking out the trash more often.
Exactly, keeping it lean and fast.
Got it. And then because this recent data is hit so frequently,
Yeah.
they also implemented frequent read repairs.
Right, to ensure strong data consistency.
Yeah, because this is the data that's constantly being accessed and updated.
Okay, so what about the other side, compressed VH?
So for compressed VH, the priorities were different.
Okay, how?
Storage efficiency was paramount.
Okay,
So they perform compactions much less frequently,
makes sense.
which reduced the overhead on the system.
Us work for the system.
Exactly. And read repairs were also done less often since
Yeah.
immediate consistency wasn't as critical for this archival data.
Right, it's not like you're accessing it all the time.
Exactly. But the biggest optimization here was the data compression itself.
Right.
By significantly reducing the amount of storage needed for those long-term viewing histories, they could manage this immense volume of data much more cost-effectively.
Okay, so now we have efficient compression, but I'm thinking about those power users. The people who have watched thousands of movies and shows over the years.
Yeah, the super viewers.
Yeah, did those massive viewing histories present any challenges even within compressed VH? They absolutely did.
All right.
Because even with highly compressed data, it can become unwieldy to manage if a user has watched tens of thousands of titles.
Yeah, that's a lot of data.
It is. And reading and writing a single massive compressed file for these super viewers started to become a performance bottleneck.
Okay, even for those less frequent accesses to their older history.
Exactly.
So did they do?
To tackle this, they introduced something called chunking.
Chunking.
Yeah.
Sounds like breaking down a big problem into smaller pieces.
That's exactly what it is.
Okay, tell me more.
Instead of storing an entire user's long-term viewing history as one giant compressed blob,
Okay,
they started splitting it into smaller, more consistently sized chunks.
got it.
And they distributed those chunks across multiple nodes within their Cassandra cluster.
Okay, so spreading it out again.
Yeah. And they use metadata, which is essentially data about the data.
Okay, data about data.
Yeah, to keep track of which chunks belong to which user and what version of the data each chunk represented.
So it's like a table of contents?
Yeah, kind of like that, yeah.
Okay, so when they needed to access a long viewing history, they'd first look at this metadata.
Exactly. They'd figure out how many chunks there were,
And
then
yeah.
they could fetch those chunks in parallel, grabbing multiple pieces of the history simultaneously.
Okay, so it's like downloading multiple files at the same time.
Exactly. And this really sped up the entire process.
Okay, makes sense.
Compared to downloading and decompressing one giant file.
Right.
And when new viewing data came in, they could just write the new chunks without touching most of the existing historical data.
So it's like updating a specific chapter in a book.
Yeah, a good analogy.
Instead of rewriting the whole thing.
Exactly.
Okay, so it sounds like they had a really robust system in place with live and compressed and chunking. So what was the next major challenge that forced them to evolve yet again?
Well, two big things happened around the same time.
Okay.
Netflix's massive global expansion.
Right.
And the introduction of those video previews.
Oh, yeah, those little auto-playing snippets.
Oh, yes, exactly.
Okay, so tell me about the global expansion.
So Netflix launched in over 130 new countries.
Wow.
And they had to support over 20 languages.
Okay, so suddenly a much bigger audience.
Massively bigger.
Okay, and what about those video previews?
So while these previews are great for users, they generate a huge amount of data.
Really?
Yeah, Netflix reported that previews accounted for 30% of their total data growth every quarter.
30% every quarter? That's crazy.
Yeah, think about that. Almost a third of all new data was coming from those short clips.
That is mind-blowing.
It really shows how seemingly small user interactions can have a huge data footprint.
Right, and so this put a strain on their existing system.
Exactly.
Okay, so how did they adapt?
Well, when they analyzed the performance, they identified several areas of inefficiency.
Okay, what were they?
So first, the system treated all types of viewing data the same way.
Okay.
So a 5-second preview was stored the same way as a 2-hour movie.
Oh, wow.
Even though their usage patterns and value were very different.
Right, it's not really the same thing.
No, it's not.
Okay, what else?
They also realized they were storing language preferences redundantly.
Okay, so my choice for subtitles was being stored multiple times.
Yeah, every time you watch something with subtitles, that preference was recorded again.
Oh, wow, that's inefficient.
Very inefficient. And then their client applications, the apps on your TV or phone, were fetching more data than they needed.
Okay, so it's like downloading a whole encyclopedia when you only need one fact.
Yeah, good analogy.
Okay, and all of this led to unpredictable read latencies.
That's right, especially at that critical 99th percentile.
Those worst-case scenarios.
Exactly, and those can really impact the user experience.
Okay, so it sounds like their existing Cassandra setup, even with all the optimizations, was reaching its limits.
It was, and remember, at this point, Netflix was already operating one of the largest Cassandra clusters in the world.
Yeah, so scaling up further wasn't really feasible.
Exactly, they needed more fundamental redesign.
Okay, so tell me about this new architecture.
So the core principle was to categorize data more intelligently
Okay.
and store each category in a way that was optimized for its unique characteristics.
So a more tailored approach.
Exactly.
Got it. So what were these categories?
They landed on 3 primary categories. Full title plays.
Okay, full movies, full episodes.
Exactly. And this was seen as the most critical data because it powers things like resume watching recommendations and engagement metrics.
Okay, the core stuff.
Yeah. Then there's video previews.
Okay, the short clips.
Right. And finally, language preferences.
Okay, so instead of embedding that with each viewing event, they're storing it separately.
Exactly. Much more efficient.
Okay, so 3 buckets for different types of data.
Yes.
So what did they do next?
The next step was sharding.
Sharding, we talked about that before, with horizontal partitioning.
Right, but here they took it much further.
Okay, how so?
They split their data storage across multiple independent clusters.
Okay, so multiple clusters instead of just one.
Exactly. And they did this in 2 ways. First, they sharded by data type.
Okay, so each of those 3 categories got its own cluster.
Exactly.
And what's the benefit of that?
Well, now they could fine-tune each cluster independently.
Okay.
So the full title plays cluster could be optimized for ultra-low latency
Okay.
for that smooth playback.
Exactly. The video previews cluster could be tuned for high write volumes.
Okay, lots of short clips coming in.
Yeah, and the language preferences cluster could be designed for minimal storage.
Makes sense.
And the second way they sharded was by data age.
Okay, so within those data type clusters, they further divided things up.
Yeah, they created 3 time-based clusters.
3 more clusters.
Yep, the recent cluster.
Okay, for recent data.
Yes, optimized for super fast reads and writes.
The most active data.
Exactly. Then there's the past cluster
Okay,
for data that's a few months to a few years old.
got it.
And finally, the historical cluster.
For the really old stuff.
Yeah, this one stores highly compressed summaries of viewing history going back many years. So it's like a tiered system based on how recent the data is.
Exactly.
The freshest data gets the VIP treatment.
Precisely.
Okay, so with this new architecture in place, what kind of optimizations did they implement?
Well, lots of them.
Okay.
First, they improved storage efficiency.
Okay.
They started filtering out those super short video preview plays.
Okay, so if you just clicked on something for a second and moved on,
Yeah, they didn't really care about those.
it's like accidental clicks don't count.
Exactly. And they also started storing language preferences only once per user.
Okay, just the initial preference and then any changes.
Yeah, just the deltas.
That makes sense.
And they implemented time to live policies.
Time to live?
Yeah, or TTL.
Okay, what's...
It basically automatically deletes data after a certain period.
So data that's no longer needed just gets cleaned up.
Exactly. And of course, they continued using separate uncompressed storage for recent data and compression for older data.
Okay, so they're being very strategic about how they store things.
Very strategic.
Okay, so what about retrieving data? How did they improve that?
So they redesigned the whole retrieval process.
Okay, tell me more.
Requests for recent data are now directed straight to that recent cluster.
Okay, the fast lane.
Exactly, ensuring the lowest possible latency.
Makes sense.
For older historical data, they implemented parallel reads.
Parallel reads. What's that?
It means querying multiple clusters simultaneously.
Oh, so it's like having multiple workers fetching data at the same time.
Yeah, a good way to think about it.
Okay.
And even when you request your entire viewing history,
Yeah.
the system can now fetch the relevant data from different clusters and stitch it all together.
Wow, so it's like a jigsaw puzzle.
Kind of like that, yeah.
And then they automated the movement of data between clusters with data rotation.
That's right.
So as viewing records age, they're moved from the recent cluster to the past cluster.
Yep.
And eventually to the historical cluster.
Exactly. And they use parallel writes and chunking during these migrations.
Okay, so they're using the same techniques for moving data around. And what about caching? Did that evolve too?
Absolutely.
Right.
They restructured EV cache to mirror this new multi-tiered architecture.
Okay, so caching is also tiered now.
Yeah, and perhaps the most significant innovation was a new summary cache cluster.
Summary cache cluster.
Yeah, this cluster stores pre-computed summaries of viewing data.
Okay, so they're not calculating these on the fly every time.
Exactly. They could just fetch them from this super fast cache.
Wow. And how effective was this?
They reported a 99% cache hit rate.
99%. So almost every time they need a summary, it's already there waiting for them.
Precisely.
Wow, that's impressive.
It really is. And this dramatically reduces the load on their Cassandra infrastructure.
Okay.
And it contributes to that smooth Netflix experience.
So it all comes full circle.
It does.
It's amazing to see this evolution from that initial Cassandra approach to this highly optimized multi-layered architecture.
It highlights the challenges of operating at Netflix's scale.
Yeah, it's a testament to their engineering team.
Absolutely. They're constantly innovating.
And all of this translates into a better experience for us.
Exactly.
Seamless playback, accurate recommendations. It all hinges on this intricate data dance.
It does.
And what's really fascinating is that these principles aren't just specific to Netflix.
Yeah, right.
Understanding data usage, categorizing it, optimizing storage, these are core challenges in data management.
Exactly.
So for you, the listener, think about how these principles might be relevant in your own work.
Yeah.
Or even how you manage your own digital information.
Good point.
Maybe this has sparked some curiosity about time series databases or distributed systems.
Yeah.
The quest for efficient data optimization.
It's a fascinating field.
It is definitely something to ponder and explore further.
I agree.